This is the third installment of my interviews with like a bunch of different friends of mine that are machine learning experts. So for this episode, I'm actually really excited to have a good friend of mine from back of my Microsoft days, like Ray Kumar, who's currently still an NLP scientist at Microsoft. So what I really generally like about Rave is that like I don't necessarily just think of him as a scientist. Like, I think he's a person who understands like the product impact of his technologies and kind of can think a bit out of the box as to what research is interesting. So that's Rave. Like Rave, glad to have you.
Yeah, thanks for having me.
Yeah. So okay. So just like a sort of like baseline here. Um, I feel like, for the most part, when I look at NLP research today, like the vast majority of it has sort of, like I would say, evolved or maybe devolved to like these sort of like large scale language models. So before we talk about like their pros and cons and what they're really about, like, do you mind kind of
Mhm.
just introducing for the noobs on the stream, like what is language, what's a language model, and then what's up with these large language models and why are people in the community so excited about them in general?
So I guess without just in layman's terms,
Mhm.
language model, you can just think of it as given some context and given some words, like in a sequence, can you predict the next set of words? So can you assign a probability essentially to a sentence or to a set of words? And that's a very like vague definition, but it's also a pretty vague um, like it is supposed to be vague. There's like a lot of different ways you can go about defining what like a language model is. Um, with the large systems, so a little bit of history, like language models have been around, like or language modeling has been around forever. Um, I think like the very first some of the earliest language models are like Markov systems where or like chains where you just say what's the probability of a word given just the one previous word. And all they did back then was they had like a table of all words in a grid, and then they just looked at the conditional probabilities of each word given the previous word. And that's how you would, and then you just keep multiplying the conditional probabilities, and you'd get some probability at the end. But that was really simplistic because you make a lot of assumptions about how sentences are created, all the like latent information, so like word meaning and word structure is just ignored. It's just depending on the previous word that you assign as probabilities. Now with these larger systems, you have this much more complex set of assumptions that are baked into the system. So is set like essentially you can think about it as the probability that you're assigning to a set of words or a sequence of words or like a sentence or like a paragraph or book or whatever is closer to some true probability. And no one knows what that actual true probability is. It's all empirical.
And so like I think you mentioned a couple of interesting ideas here. So the first one is you mentioned a lot of these older techniques are like count based.
Mhm.
But then like it also seems like that's the case for for the larger language models based on your description. And then I also want to touch on another point you made, which is that you're saying like this idea of a true probability, but really like is that really a knowable thing? Like it's just like you have to derive, what the true probability of a word is from data. So I'm wondering how would you really go about defining what is the true probability?
Well, if you know the physics of language, I guess, like if you think about it that way, or if you're God, you probably can get to the true probability. But there's this really interesting book by Steven Pinker called The Language Instinct that people should check out if they're into
Hmm.
language. And that book, you can read it if you even if you have no idea about NLP or you've not taken any math classes or anything. It's just a well-written book dealing with language, and then it goes into NLP just a little bit and computational linguistics, like it hints at it,
Hmm.
but mostly just deals with how we as humans understand and use language. And a couple of things that he pointed out were that language is something that seems to be baked into our brains as like some sort of circuit or like set of circuits in our brains. And it seems to be this thing that is, at least some part of it or some like foundational element of it is biological and not just purely cognitive. And I think like one example of that, and this is one of my favorite examples, are the American Sign Language, ASL, is a really nice language for people who are deaf, and it has a very consistent and usable grammar, and it's congruent to like English and these like other now like very developed languages. But in poor areas of the world where they didn't have these resources, I think it was somewhere in Africa, but I forgot exactly which region. They didn't really have like a formal sign language system set up. So these people who were deaf, they just kind of like made a really bad version of sign language. But after a couple of generations, it kind of evolved by itself into a very usable, very consistent language without any outside input. And the same can be said for when slavery was a big, well, it was a kind of a normal thing in America and in like the Western continents. They would bring slaves over from a bunch of different regions of the world, and even like a bunch of different regions in Africa where they never interacted with each other, Africa and South America, and they never interacted with each other. And so their languages would be completely different. And when the first wave of slaves were brought over, they couldn't communicate with each other because, again, their languages were so different. But after a couple of generations, their languages were able to mix, and they again developed a very consistent, very usable language without any input from like a grammar teacher or someone trying to like actively develop a language. And so it seems that whatever your starting point is, if you have a large enough population and if you have time, the language just kind of settles into these almost predefined like systems, at least like on a very basic level.
I mean, like, like this is an interesting point, and I think it's something that pretty much any tourist has somewhat experienced, where like you can, go to a foreign country, you have no idea like what the customs are, you have no idea
Mhm.
like what are the memes in that language, but you can kind of get by like waving your hands and smiling
Right.
and all these sorts of like universal symbols to get by. And so I find this interesting because like on one like what I hear you sort of getting at is that there's this sort of like uber level language, that
Mhm.
like all sub languages map to, and maybe the machine learning efforts should be done should like work across languages naturally as opposed to be segregated across languages. um and so I mean, let's talk about that for a bit, because like I don't believe there is data for such an uber level language. Like what you can observe is just the language, like the languages, right? Not
Mhm.
the super level language. And so like I mean, and I'll ask you like a very similar question throughout this interview, in that, like, given unlimited time and unlimited bandwidth, like like how would you address this problem? Like, if resources wasn't an issue for you, how would you solve a problem like this?
So I guess machine learning has a lot of different forms. One is you can observe only from data, um, which is in this case to learn that like base language, if there even is one, that would require like way too much data. But also, it seems that that base language might be learned, like you said, like if you go to like a foreign country and you just have no idea about their language, you can still get by with kind of like physical actions
Hmm.
and things that just seem kind of like the right thing to do, with people. And it seems that like those kinds of physical cues are also like if you're interacting with a dog or like a horse or like a cat or like any mammal that at least is somewhat social, um, you can kind of know before you get to know that one particular animal, like what physical cues might set it off. Like you can kind of figure, like know, okay, if I posture aggressively towards this dog, it'll convey aggression.
Hmm.
And that'll be the exact same thing for a human, right? So like it even seems like between species, there's this interesting common set of ways of communication. And I think when it comes to humans, people use those ways of communication to then go back and inform like the actual language, like word based language, like spoken language or written language. Does that answer your question? I think I
Um,
went off on a tangent.
no, okay, no, no, like this is an interesting point. So I mean, let's think about. Let's just go down that rabbit hole for a few more minutes. Um, so so let's say in the case where you're really trying to learn the meaning of a word, right?
Hmm.
And if you assume, like, maybe we tend to think of this analogy of humans being sort of like machine learning systems just because we kind of understand machine learning well now. But there's this idea where, like, there's some stuff that I don't need to communicate to you. Like, let's say, even if you and I, didn't grow up with, like, let's say we grew up in very different countries. Let's say neither of
Hmm.
us spoke English. We still know that, if we look at each other and we glare with our eyes and we show our teeth, that this is a sign of aggression. And
Right.
so, on one hand, like, like that kind of makes this theory that, like, we are just sort of these data processing engines that consume data around us to make decisions. Like, I think
Hmm.
that makes this theory a bit void. But I think the more interesting part is, like, maybe then, like, you can't just think of yourself as the machine learning engine. Like, it's your experience plus evolution. So basically, some sort of past sum of all of your experiences that would somewhat explain why we both understand why an aggressive glare is aggressive,
Hmm.
even though, like, we haven't necessarily explicitly seen data to observe this phenomena.
Yeah, I think so. I think like on one hand, we do seem to be kind of like these data processing machines, but it seems that because of evolution, we have a really nice set structure and how we take in data.
Hmm.
And I think that like if I had, I think going back to your previous question, if I had like unlimited resources, I would try to find that function in humans and look at not just like statistically model the output of that function over many different humans.
I see. So I guess, like, another thing you're saying is that, like, you feel like a lot of NLP has been too black boxy. Is that correct?
I think so. I think like because of the sheer amount of data that humans produce, we can afford to be somewhat black boxy.
Hmm.
And it's clear, like with like transfer learning and stuff, that we are learning some of these like linguistic commonalities.
Hmm.
But I think there's also a bias in how we're learning that. So, for example, there's racial and gender bias in
Hmm.
NLP, um, but there's actually no racial or gender bias in when like a child is born and they just learn to speak. Like it's all culturally introduced, right?
Hmm.
And culture isn't something that's like baked in to our like brain circuits when we're born. It's learned, right? And
Like, I've always found this problem interesting, but I've also found it very challenging in that, like, even if there are, like, if there's a mismatch between our current culture and our data, which is basically our past culture, like, what's sort of a way to kind of address this problem at scale? Because I guess, like, the non-scalable solution is you recorrect the biases manually, but that doesn't seem like something that you can just programmatically add on top of a language model without humans being
yeah,
involved. And so, how do you see this problem solved in a somewhat automatic way?
well, it's actually really difficult, and that's where the limits of NLP still are.
Mhm.
Even with like companies like Google, which I don't work for,
Mhm.
so I can speculate more about what they do.
Yeah.
So I know for a fact they have block lists in their. So they have this model called Google has this model called Smart Compose,
Mhm.
and I think it was either in their blog post or in their paper, or maybe I spoke to someone. But
So do you mind just introducing, like, what this model is and
oh,
why it's
sure.
interesting?
Yeah. So many of you, if you use Gmail, you probably like have interacted with it already. As you're typing, Google will or Gmail will suggest what you might want to type next, and you can just hit tab and it'll autocomplete for you. And it's better than your phone because it seems to be able to autocomplete longer segments. And this, you might, for someone who has no computer science experience, might look at this as, oh, like they're somehow like tracking my data, or they're doing something really specific to me. They're looking through my mail, and yeah, they are kind of, but the part that is really specific to you, they actually keep wrapped up in your own mailbox, and nobody else has access to that. But the cool thing is, most of the model is powered by combining your data with like hundreds and thousands, like millions of others' data, and not just email data, but like a ton of other data, to the point where like no one can distinguish what your data, if it's in there, with anyone else's. And they learn this model that essentially is like some average of like all of this data. And based on that, they kind of know what you're about to say, because most people kind of talk the same regarding most things. And so like what you'll see that's completed on your email, I'm willing to bet is either phrases that are really common, which that's from like the huge model that kind of averages everyone's data, or really specific. And that's when it's really specific, Google is just basically looking through your mailbox and auto completing it, but that data kind of never sees the light of day in terms of like all the rest of the people.
Yeah, it's interesting
Uh,
because I can imagine there's like an easy way to test out this theory where, like, let's say I type in in Google, like, I want to, and then it autofills like meet with you, then that
mhm,
sounds generic enough. But if I type like I want to meet with Rave, and then it autocompletes to like Ramesh Kumar, then I'm pretty
mhm,
convinced either all the Raves have a last name of Ramesh Kumar, or they're just
right.
like reading my mailbox to figure that information out.
Yeah.
Um, and so let's talk about this for a second, because like most of the efforts I've seen around language models tend to treat, like, there's like they consume Wikipedia, or like they consume like some other like large textual data set. So how does this work exactly? Like this idea of fine tuning a language model on private data, how does this work really? And I like specifically.
So a good thing about Wikipedia, for example, is that it's essentially a collection of facts. And so without using really complicated, interconnected like services or structures, like you can say like a cardinal is, and then statistically it might autocomplete to red. Because when you, or like let's say you try to bias it even more, saying the cardinal, which is a bird, has the color red. And so what's happening there is there's very few pages about cardinals. And then when you look at a cardinal, you might think, oh, is it a bird? Is it the religious thing? And then you introduce the word bird. And so that cuts down even more. And then you introduce the word color. And then basically the words that are kind of really close to those three words in terms of what has appeared on Wikipedia, there's very few other words at that point. And so it might get to red. And so you can do, and the point of training on Wikipedia is that you can get to those kinds of, you can learn those kinds of like statistical closenesses, I guess. Like that's how I would like to think about it. Or like that kind of like that landscape, with like kind of a simple, or like a singular model. And what was your other question?
Yeah,
How it
so so
affects?
so so, so like let's pause for a sec, because like my question was really about how to fine tune language models on private data. But I think
Right,
like the point you're making here is that, like, well, there's sort of these ontologies that you can learn from data, like sort of facts, right? Like,
right.
like cardinals are typically dressed in red, for example. Like that's close to being
Mhm,
a fact. And so, like, let's pause and go. Like, I want to ask you a question here. So, typically, like the way like I've seen this done in the NLP community is that you vectorize a word,
mhm,
and then like the proximity of different words can, indicate in vector space, can indicate proximity in meaning space.
mhm,
However, if I look outside of the NLP community, like let's say in the more information retrieval and search community, so people that build search engines, a lot of them talk about ontological graphs. Like they talk about words being related to each other in some sort of graphical sense, where,
Mhm.
red is related to colors, colors is related to clothes is related to people, and a type of people is a cardinal, and then that way you can kind of derive this meaning path as opposed to a meaning vector. Have
Mhm.
you seen anything in the NLP community that would indicate that graphs are a better representation of words than vectors, or do you feel like this idea of a vector to represent the word is here to stay?
Again, I think like it's really kind of like interconnected, and that's where I get disappointed when I see systems using only one or the other. Graphs are obviously important because they have a really cool structural representation of knowledge. Um, but like really it's hard to you can start blurring the lines between graphs and vector spaces. So like if you learn a vector space of a bunch of different words using a bunch of different data, you can build a graph out of it, and that's actually sometimes how some of these graphs are built. They start with a vector space and they reconstruct the graph. But let's say you have like an expert in like a history expert who's super super focused on like one particular like period in history. The knowledge there is actually quite limited. So like it's both like it's both limited and like kind of unlimited, right? Like so like if you have someone whose niche field is some like 1 year in history, there's like an unlimited amount of knowledge in that like you can go through every single thing that happened in that 1 year down to like how like where people walked that day, like a single person's life, and then like how his interactions affected kind of everything. Or you can kind of zoom out and there's like kind of a smaller set of like more abstracted knowledge. And so when you're dealing with kind of countable and finite knowledge, and that countable finite knowledge is also a small set, it actually might make more sense for you to make a graph or some sort of knowledge structure that you can just say, this is it. This is all that I want to or need to learn about this, about like this set of things. And so in production or like in use, when you want to use this knowledge, the model simply needs to look it up. It doesn't need to like try to learn anything past that.
Hmm.
But when you're dealing with like vector spaces, in my opinion, the whole point is that there's an infinite set of knowledge, and and it's and it does exist on a continuous space, and you're trying to define the space such that the distances in between vectors make like kind of make sense in some way. And people still actually don't have a great way to define the spaces in between vectors. But we're trying,
Hmm.
and that's where like a lot of these like for these some of these models like these like transformations are these continuous transformations, which are then at the very end or like it maybe in like steps between are cast into these discrete spaces. So one example that I like to think of is when you're defining a rectangle, like the idea of what a rectangle is. You only need two vectors to describe it. You just need a height, or not two vectors, two axes to describe it in like your knowledge space. Um, a height axis and a width axis. And that's assuming that this is a very abstract rectangle that's not in like the real world, and it has no orientation. It is just a rectangle, and so that's incredibly like simple. And then maybe you can add like another axis if you want to define a new aspect of this rectangle, which is orientation. And then you can add another axis if you want to define like color or something.
So,
Um, and so like
like it's interesting you mentioned this because you've kind of reminded me of one of my favorite like sub areas of reinforcement learning, which is like
mhm,
representation theory. It's not really an area of, it's more of a mathematical area, but let's say, you want to describe a circle, you could either describe it with an infinite number of points or you could describe it with like a center and a radius. And
mhm,
that does the same thing. But figuring out like
Well,
what
does it
those
do the same thing though?
representation,
Like it might actually not do the same thing.
well, like what do you mean?
In terms of, I think this is where it gets tricky. Like in terms of the use case, so like when you describe a circle with a infinite set of points, you're actually describing, in some cases, you're giving more information about the circle than the radius and the center. Um, because like now you're describing exactly where those points might be
Mhm.
in like actual physical space, right? Whereas with a radius and a center, you might, or like let's say maybe even just with a radius, maybe like with a center, you might achieve the same
Mhm.
thing. With a radius, you're kind of achieving, you might actually be losing some information.
Yeah, like it's a sort of a position agnostic representation without
Exactly.
the center. Yeah, like I understand that. That's interesting. And so, but here's the thing. Like I would even argue that like in math alone, I don't see this being a tractable problem, let alone mathematically, let alone philosophically. It's just, by virtue of more people exploring, you get these like people understand these relationships. Like, do you really have faith that computers can help here, like, or that any NLP technique would help solve some of these problems?
Well, I think empirically you can say you actually can because we're just like bags of meat with circuits in our heads. And
Mhm.
so if you take that view and you take the view of like there's nothing really like mystical about us, then we are also finite, except that our brains work in continuous spaces. And so somehow evolutionarily we're able to model and understand these. And so if we can, a computer should be able to. It's just that we haven't found I would say we haven't found the right representation. For example, in NLP, there's not a debate, but like there is this common thing of when you're making vector representations or when you're trying to construct a vector space of concepts or words, and that's called like a distributional way of like representing knowledge. Um, you you start off with some length of vector, like let's say like 300 or something, and then if you really want to get into it, you can just retrain your model over and over again with different vector lengths and just see what gives you like the best results on some held out test set.
Sure.
And if you do it like few enough, if you don't overdo it, you won't like relearn the test set, and you'll kind of actually get like the most optimal model. But all you're doing is you're just like chopping off or adding new axes, and each of those axes actually does mean something. We don't know what it means, but by virtue of how our math works, um, you are kind of asserting when you do that. Let's say you choose like a 300 length vector that you're trying to learn for every word. You are kind of making an implicit assertion that there's 300 unique and independent axes of knowledge or like axes of like representation that about this one word or this concept. And that's really hard because on one hand, it's like 300 sounds like quite a bit. Or it could, for some other applications, it might seem 300 is not a lot at all. And so when you have these um, massive vector spaces, you might you might be overlearning things. So like there might be a lot of like non-independent axes that you're learning. Like you might be like re-representing knowledge over and over again, which is like a non-efficient representation. Or you might not be capturing just enough information about this concept or about like concepts in general. So like for example, you can represent the whole universe using like let's say like atoms are just the end all be all kind of thing, like the very smallest thing, like not even going like subatomic or whatever. You can represent maybe the whole universe using just atoms. And
Mhm.
technically, if there's nothing else, and our brains are just like made of atoms, if you capture atomic positions, then you've kind of represented the whole universe. And you can do that with just three vectors or three axes basically.
Yeah, so I guess like while like this is more of the difference between representation and then the algorithm, right?
Hmm.
Even if you figured out the representation in this case, and it could just like theoretically be three vectors, it doesn't mean you figured out the algorithm. And like the counterpoint to that would be something as simple as, well, like even if you were to arguably say that like, well, there's only 300 axes of meaning, well, like the fact of the matter is that like we still don't know how many new ideas are being generated each day. And so it's not just a static thing, it's in fact this thing that explodes in size over time. And so you could make the argument that like all new ideas are some subset of old ideas, but like
Hmm.
that for me doesn't seem like that doesn't feel true either, just because I see new ideas being proposed all the time. And so if anything, like I like like the counterpoint is like, well, why 300 axes? And I would say to that, well, why not like a million? Why not an infinite number of axes? Like why isn't that a better representation for meaning?
Well, thinking
Um,
about it, a lot of these new ideas that we've come up with over the past, like let's say 2,000 years,
mhm,
they could all be understood by people 2,000 years ago. So looking back at it, so if all the new ideas that we've come up with over the last 2,000 years can be understood by people 2,000 years ago, like if they're willing to understand it,
mhm,
that means that there wasn't any fundamental changes in our brains
mhm,
such that new avenues for information were added in our brains. So like we can hold the same amount of or the same types of information, right? Like
mhm.
our brains didn't suddenly develop like larger vector spaces for like or like representational power over the last 2,000 years, right? And so I think that's where I would be really interested in NLP is how did we come up with all these ideas in the last 2,000 years without changing our representational power in our brains?
Interesting. And so like this kind of makes me think of uh, so like let's say in reinforcement learning, for example, this idea, like it's been a long ongoing debate that some people tell you, you need more structure in the problems, like you need to somehow embed like knowledge of a physics engine into your RL agents, or embed knowledge of past games, or embed knowledge of past play, or etc.
Mhm.
But for the most part, while this sounds correct, like it makes sense, like more structure should help. But in fact, if you look at experimental data, that's not the case. And in fact, just throwing more dumb compute at a problem seems to be better than injecting any sort of structure into a problem. And so it's easy to say, like, well, like, but eventually this trend is gonna die off, but it doesn't seem like it's dying off. And like now with these huge models like GPT-3, I would expect we're still gonna have multiple more generations of these large models that are gonna outcompete anything that's hand coded. So like at this point for me, it's harder to justify this belief that more structure would help, just because I've consistently been wrong over the past 10 years based on this belief. So how do you rationalize it?
Well, an interesting thing about like GPT-2, for example, which you can kind of like take these ideas and project them onto GPT-3 or like whatever new massive models come out, is you can learn most of the information if you train GPT-2, for example. You can take that, which is, and for those that don't know, GPT-2 is like this. GPT-2 is massive language model, massive in terms of like the number of like nodes and connections. And you can boil it down by taking the input of GPT-2 and the output of GPT-2 and using those two input output pairs, using that input output pair to train a smaller model that then learns most of what GPT-2 like quote unquote knows. And so that means that with smaller representational power than, or like internal representational power than GPT-2, you've learned most of what it knows. And so what that, and
So sorry to interrupt you here, but here, are you referring to the network distillation work, or is there some other
exactly,
method?
yeah. So it is called distillation.
So do you
Uh,
mind elaborating on this point? Because I think for me this is a fascinating subfield of NLP. So do you mind just kind of describing it at a high level, how it works? Why do you think it
Sure.
works?
Just like the basic idea is that you can take an extremely complex model or like an extremely complex space of or like method representation, And using that like learned or trained model, you can train another model with a much smaller, with a much like lower complexity or like a much smaller representational power, using only the inputs and outputs of the large model. So now, without looking at any actual data, you just take the same inputs that that large model had, and now you only look at the outputs of that large model, and you train the smaller model. And generally, what seems to be happening is that when you train this very large model, it captures a ton of nuances in the data, like a lot of distributional nuances that come with having a massive amount of data and words appearing in many, many different contexts. And it boils it down to um, some finite set of like independent representations, basically like it casts it into some like final vector space. And so
So
it cuts down on like it takes reality and it boils it down a little bit. And so what happens is then you can take that boiled down version and you can boil it down even more into like a simpler model. And what you retain or the model performance is actually better than how much you boil it down, if that makes sense. So like by boiling it down, like maybe to half complexity, you don't lose half the performance.
So that's interesting. Like, have you seen any work on stacking distillation architectures? Because to me, it sounds well like you look at the first model and it's distilled, then distill the second one, then distill the third one, and do this like, ad infinitum. Like, do you believe this would be one way to enforce sparsity, or just you think like that would just reduce to uh,
I think like
distilling
essentially
inputs?
what you're doing is you're making a copy of a copy.
Hmm.
And so if you do it enough times, you'll get kind of like a really shitty copy.
Hmm. The
Um,
broken
but
telephone game.
Yeah, like if you have a really good copier though, maybe that first copy is not so bad. And you've taken this 3D, let's say like you're copying your hand or something,
Hmm.
you're taking like a 3D space and you're projecting it onto a 2D space as long as you, the user of this 2D space, thinks that, just 2D is useful in this case. I actually don't need the full 3D representation of this hand. Maybe I just need like just the fingerprints or something, just like the contours.
Mm.
And so if you have that, like maybe for you it's fine, but you're obviously gonna be losing something, right? But actually, what this shows me though is that you're already taking something that. But for me, like the better point of distillation is you're taking something that's very like real, like your real humans from their brains wrote something like on the internet or like a book that was used to train this model, and you're boiling it down into this finite representation. But what it proves that most of that knowledge you can use using a simpler representation. And so that shows me that adding more complexity to a model is going to get you marginal returns. But I think like one thing that we haven't looked into as much is now that you are starting to get marginal returns on complex like model complexity, can you maybe augment that with more structure and start getting much better model performance or like
Mm.
much better like modeling of reality?
Well, like what I find interesting, like I definitely agree with you. Like philosophically, I agree with you. But then, I keep seeing this new work that disagrees with this bias. Like let's say when I don't know if you got the chance to skim the paper, but when I skimmed the GPT-3 paper, for example, I was surprised that they didn't even use sparse transformers. And it's kind of like, well, like OpenAI, I believe, also had invented them. And so it seems like even though there is this interesting work around sparsity, like when it actually comes to beating state of the art, the people who are also advocating these very same sparsity algorithms are not actually using them themselves.
Well, I think that's
Why
like
do you think that's the case?
well, I think that's kind of like survivorship bias. I think like the fact that they didn't. I mean, I actually didn't read that paper. So like, did they say that? Because for me, like just I'll just put it out there. Like
Mm.
transformers aren't that interesting.
Mhm.
As a person that like is
So actually, before you say that they're not before you say why, do you mind just at a very high level describing like what they are? and then go into why you think they're not very interesting?
Sure.
Just like very
Like
high
just
level.
just from like a mega high level, you're
Mhm.
just basically encoding some output, decoding it, encoding it, decoding it, encoding it, decoding it. And you just keep doing that. And you just kind of like, again, this is like the dumbest way to describe it,
Mhm.
but you just switch up. Like there are many different methods of connecting inputs to the outputs in terms of how, like what functions run
Mhm.
on what inputs. And you just build this like long chain and you increase the amount of representation, and
Mhm.
then you find that you get some output. And
Mhm.
when you have some metric that's supposed to measure how good that output is, you find that these transformers do a really good job of maximizing that metric.
So, so,
And
so,
so
we, so we have a question from chat here, and I
Mhm.
somewhat agree with this question. It's basically so pseudomains is asking transformers versus LSTM because I believe the way you've described it so far, to me, sounds very similar to an LSTM. So, how should people understand the difference between these two architectures?
So a transformer, especially like the ones that perform really well, they kind of are able to look at, just on a very high level, like kind of look at the whole input space at once at each like encoding decoding step,
Mhm.
rather than LSTM, which forces the input to undergo some transformation, and then you can also like have that input flow through to different nodes in LSTM, but it still might be transformed in a way that now you no longer have any idea of like the actual original transformation. And when people saw that that might be a problem, they invented things like attention, which is like where transformers came up. In any case, where after the LSTM goes, after the information flows through like all the nodes of the LSTM, you can have the final output be informed by each node instead of only like the last node. But even then, you might still be losing some information, or you might not be representing it with enough like representational power. And that's where transformers do really, really well. Is that you can essentially just throw a ton of compute at it. You can say, hey, maybe just try not to ignore too much, or like just, in my mind, that's how like I like to think about it. Just try not to ignore or lose too much information, and make your output be very informative of the different stages, or like the input. Let the information flow like as freely as possible through the
Mhm.
whole structure and through the series of transformations, and see what you get.
So let's say, I mean, I was an alien brought to Earth, and like I didn't have any biases on what good NLP research should look like. To me, at least, like the transformer architecture actually seems more intuitive than LSTM, just because like looking at the meaning of a single word should be somewhat dependent on, like, let's say we're doing something like translation.
Mhm.
Then me figuring out how to translate a certain word should be dependent on all other translations of all past words, and not just the end level translation of a sentence.
No, I totally agree.
So why is this bad? Like, I mean, like, why
No,
shouldn't we continue on this
it's
trend?
not bad.
Okay.
So in terms of like, if you're looking at performance, yeah, transformers totally like blow LSTMs out of the water. And
Mhm.
I'm not advocating that we use LSTMs over transformers, right? Like use what works basically. But as a person who's privileged enough to not have to like only do research that needs to push the cutting edge, and as a person that can afford time to just think about what NLP means to me, and like think about how we should progress in general, it's that cool. Transformers is an awesome concept, and now that it's there, I don't find it like too interesting to then further build on just making better and better transformers. And
Mhm.
that's what I was kind of talking about in like the previous conversation, or like topic, I guess, which is when we start getting these marginal returns on these very complex structures. I think it's time to pause and say, okay, we did a really good job using transformers, but now the returns are marginal, and it still seems like we can't do basic things like summarize like a paper, or like summarize a movie. Why is that? And so it might be that we're still not encoding information correctly. I think like that fundamental encoding is what I would like to see explored next. And transformers actually might play like a big part in that, right? It's just that when we use the same overall like philosophy of let's throw more data at it, more data of the same type, and see if by changing the structure we can learn better distributional properties of the data. I think like there's a limit to that, you know.
I mean, it does feel like we're somewhat speculating because, like, if I were to just look at the data, then, like, we don't have a good summarizer model, but that's independent of transformers and it's independent of all the more structure-driven approaches to NLP. It's just no one has figured out how to make a good summarizer.
No, I
Um,
totally agree. I think that's what I mean. There's a in the set of all people who are producing NLP research or participating in it, there's obviously like the energy is limited, right? Like that people can put into it. So I hope that the NLP community doesn't put all of its energy into only pursuing more optimized versions of like transformer configurations and puts like quite a bit of energy or maybe even like most of its energy into thinking about different ways we can represent knowledge, or different methods of like or figuring out why summarization still isn't working.
so I want to do a slight digression here because you made me think of, like, are you familiar with the concept of ergodicity?
No.
So basically, like, okay, so assume that you have, like, I don't know, 100 people that quit their jobs to start companies, and then I
Mhm.
tell you the average salary among these 100 people is $10 million. Like,
Mhm.
what's the most likely explanation for this?
So out of the 100 people, all their salaries are $10 million,
Like,
or
their average salary is $10 million. Like,
oh, probably
like
like there's like one person making a ton of money would be the
exactly, and
obvious one.
everyone else is making close to zero, right? And
Mhm.
so when I think of research, I also think there's a sort of similar effect at play where if you spend time doing the non-sexy stuff, it's probably not going to work out. And so
Mhm.
you're actually better off from a career standpoint doing the incremental work on the really sexy stuff, because
Mhm.
worst case you can go, well, like this was a good trend and I became an expert in it. Like, you're not trying to be Jan LeCun, but you are trying to, like, let's say, have a really well-paying salary at the big tech company. And so, like, how do you think, like, you break this trend? Because to me it almost seems somewhat inescapable. Like, not everyone, like, was gonna be Jan LeCun, so, like,
Yeah.
not everyone should try
Well,
to.
I think in Andrew Un's course on Coursera, like his deep learning course, he does a really good job of doing interviews with a couple of people. One of them, I think was Geoffrey Hinton was the very
Mhm.
first one that he did an interview with, and he went through some of his life. And it's that when people like Geoffrey Hinton, Jan LeCun were working on this stuff, they worked on it. It seems to me they worked on it because they believed in it, and not because it was giving them like Uber money to start with. And so it seems like when you're working on something because it's a trend,
Mhm.
or you're working on something because you also want to maximize your career, especially in machine learning where we try to like minimize our biases as much as possible. You're actually introducing quite a lot of bias because you're saying that I want to move NLP forward, but I'm going to add this extra dimension of I want to move it forward given that my career moves forward also. So you start limiting yourself in as to like what space you can explore. So for me, I'm actually not a researcher. I'm an applied scientist at Microsoft. So it actually in some ways gives me the flexibility of saying, well, I'm getting paid to improve this product, so I can put all of my efforts into just improving a product. And a lot of the NLP like research that I do that's completely separate from maybe the product I'm working on is just at home, like in my own time or talking with coworkers who have ideas, and we just kind of explore those ideas verbally and we see how those can fit in. And like 99% of the time, these ideas won't fit into a product or might only fit into the product like in like 10 years when it doesn't really matter anymore career wise. Um, but those, I think, like those fundamentally different ideas are what'll move the field forward.
Um, yeah, like that. Like, I think, like, I've actually heard Nassim Taleb refer to this as the barbell strategy, which is you basically pursue the really like popular stuff, but
Mhm.
then you also dedicate a small amount of time for the really wacky stuff. That way you're always financially secure. And if things work out, then it, then it really worked out without you having let's say spent 100% of your time on the really wacky stuff.
That's true, but then
I
you're also kind of like at that point you might be. I think there's like some cognitive dissonance there in that, like, and this is I think more about how society works than NLP or anything.
Mhm.
Is that, well, if you really believe in something and it's positive and productive,
Mhm.
shouldn't you be allowed the time to pursue it in full? And that's where it's like when at work, I don't find transformers interesting. Not that they're like a flawed concept, but because I think there are other avenues to explore that I would find much more interesting. But at work, transformers do work, and they have gains like metrics wise that are unrealized for like whatever reasons. Like even at Google, for example, right? To have like transformer everything architecture, they actually needed to change their infrastructure to allow that to happen in the first place. So what that means to me, what that shows me is that, okay, transformers work. They clearly outperform these other models in some performance metrics, and we don't have the infrastructure to productionalize it to like all of our users. And so what that means is, to maximize our user experience, we're now going to put our energy into productionalizing these transformers, which is totally okay, and like that's the right thing to do. But that also means that the energy can't be used for exploring like weird, like crazy concepts. Like, can you like make a model that's completely multimodal in nature, because humans learn through many senses and not through like literally associating letters with how many times they appear next to other letters.
Mhm. Although it would be interesting, like let's say we could fast forward like another 100 years into the future, and if this trend
Mhm.
is still isn't broken, like that would be interesting. Like what if
That would be
meaning
interesting,
is
yeah.
just like counting, and then we're kind of overthinking it, just because like we're humans and we feel like there has to be something bigger to meaning. Maybe it is just count.
Well, actually, I
So
don't think. Well, I don't think there is. I mean, like even without thinking that there's anything more to meaning, I just think that we're counting with not all of the information that we should be. Like when you teach a baby to like talk, you're clearly not just like throwing information at it, right? You are like giving it some structure, and then it's kind of making these feedback loops of taking that structure and applying it to a scenario and seeing it where it fails, and then updating its internal structure. But there does seem to be this core internal structure, that maybe like the associations are updated, but the fundamental structure itself is not updated. I think that that's like a really valid avenue for progress here. But to your point, if in 100 years we're still getting the same transformer results, like we're still getting gains with these transformers, I would be really surprised. One, because again, the gains will be marginal, and even if we get to 100% on our metric set, our current performance metrics, it would still be like quite meaningless.
Um,
Um,
like this is a great segue into one of the other questions from chat. So I think the question is somewhat directed at me, so I'm just going to rephrase it slightly. Will the IPU be the new thing in the future? So just for reference here, Rafe. So IPU
mhm,
is this a new kind of architecture that's being
mhm,
developed by GraphCore, the company that I'm currently working at. But
mhm.
I think that there's a more general question here, which is like, do you believe that part of why transformers are so popular is because GPUs are cheap and are really fast? Like, do you feel like with different hardware architectures, we could potentially get better gains on different kinds of algorithms?
Um, I th- I mean, yes. I mean, clearly, like one of the reasons why deep learning is so popular now is because it's so available.
Mhm.
Whereas before that, we hired a bunch of linguists to like actually encode linguistic structure into everything. And so none of those approaches are wrong. It's just like we're doing the best with what we have, basically.
Mhm.
So with this new technology, Could you explain how that might, how do you think that it'll change how we approach
Yeah,
NLP?
yeah. So I would say at a high level, like in like when you think of a GPU, like you have to like load the data to the GPU and then do like a
Hmm.
massive matrix multiplication because that's pretty
Hmm.
much what a GPU does. With the IPU instead, like you can have like both data and model locality like in the same place.
Hmm.
And then you don't necessarily like basically like if you like think of what's popular in machine learning that isn't matrix multiplication. So some examples are stuff like Markov chain Monte Carlo, which is like an algorithm that's CPU bound, but
Hmm.
like on an architecture like an IPU can like outperform GPUs by 10x to 100x. So this is kind of where I see the benefit, where we've basically now saying like, okay, that we have all these algorithms that work really well, and they're basically just doing a sequence of matrix multiplications. But
Hmm.
what are some algorithms that don't use that sort of like
Hmm.
model, and would they do better on an IPU? Another example, for example, is like GPUs can't do like low batch, can't train models with like a small number of batches
Hmm.
because you want to have as big of a batch as possible to fully utilize the GPU. But an IPU doesn't care. And in fact, if you load smaller batches, they've shown that you can have a model that generalizes better on transformer tasks. But again, like this is for me, this is like there's an uber interesting point here, which is, well, you don't know. Like maybe with more effort on a GPU, you can get it to outperform. Maybe with more effort on an IPU, you can get it to outperform. I don't think
Hmm.
there's a clear cut paper that will say this is better than that. It's more like with more work and kind of a more community agreement around that this is a good architecture for this stuff, then maybe
Hmm.
you can make the claim. But I don't think you can make the claim right now without lots of ifs, regardless. Like it depends, basically.
I agree. And I think like when you have these new architectures, like if it does enable new ways for researchers to like think about problems or to implement their like proposed solutions, it does lead to like new avenues to explore, which I really like.
Mhm.
So I think that's like a cool creative way to further the field.
So I want to do a brief call out to some work of yours that you shared with me yesterday. So for just for context, chat. So Rave recently open sourced like a new data set for language models that is that basically leverages some critical role, which is sort of a like a live stream where people go through D&D. So it's a very different kind of data set. Like it doesn't typically look like what we've seen with other publicly available data sets for NLP, like the Enron models and etc. And so basically, I want to ask you two questions here, Rafe. So the first one
Mhm.
is like, one, why D&D? Like, why is this interesting? And then the second question is, like, why are we so obsessed with the same data sets? Because, like, at what point do you know, like, well, maybe I'm just overfitting on this thing? But really, like, if you add lots of data sets, you can immediately know if you're overfitting because you test out, like, let's say these large models, and if they don't
Mhm.
generalize at all on D&D, well, you know that you're not learning anything interesting, and maybe the simpler models that aren't as
Mhm.
large would. And so like people like talk about this a lot, like where in industry it's all about getting more data and having simple models, but in academia it seems to be more about make the models bigger to overfit the small data sets. Where are you at, like on the spectrum? How do you feel about both of these questions?
So in industry, there's definitely like you touched on earlier, there definitely is a career component, which kind of which is unfortunate because what happens is people try to advance their careers, which is natural and totally fine. But to do that, there's like as a scientist, like there's very few ways. As a scientist working on a product, there's very few ways you can say you contributed. One of the ways is you build a better model, and how do you define better? Um,
Metrics.
exactly, and so there's only two types of metrics, which is metrics on like an offline data set, which you can obviously just keep on like gaming to do better and better if you're kind of like that. Um, or there's these online metrics, and a lot of them, when you have these marginal gains on a model, a lot of times they'll just be like kind of flat or statistically insignificant. And so one thing that the industry is learning is still how to best utilize scientists, um, and how to best like showcase their work and how to best help them in their own careers to kind of like synergize with the company mission of like better user experiences. To answer your other question of what was it? How to avoid like overfitting on these standard data sets?
Yeah.
So I would say, I think you already kind of gave the solution, which is like have a bunch of different data sets. With I think for me the important point is have a bunch of different data sets dealing with different topics, and see if it generalizes there. Don't just have one data set and have a held out set, which is basically the same as like the rest of the data, and see if it improves there. One really cool data set. Okay, so like with my D&D data set, it's really unique because it's non-business related. And what happens in D&D is there's a set group of people and they're creating a whole world and a whole story that starts from that session. So there's like almost no background knowledge. So there might be some like
Like
maybe
swords
like,
are sharp, for example.
yeah,
That's
exactly,
background.
like swords are sharp, or like everyone kind of knows what a troll is.
Hmm.
But those are kind of like easier. But like the complex stuff, like there's a castle here and I'm going to describe more about the castle. The dungeon master is kind of forced to describe that castle. So like all the knowledge, like most of the knowledge that you need to understand what's going on is actually all within the story that these players are constructing. And so theoretically, if you had a model that's actually good at building some knowledge structure, either implicitly, like with transformers, or very explicitly defining a structure, it should do really, really well on some like held out test set or some other D&D session. And there's also really interesting things like there are player actions which are determined, whose consequences or whose success failure rate is determined by dice rolls. And so what Dungeons and Dragons as a system does is it takes reality and it kind of boils it down a little bit into a more structured reality, where the actions and the consequences and the story and communication is all kind of like more structured. And of course, this is not reality again, because in reality, you don't need to roll dice for everything. But the issue is no model or architecture that exists right now can perform well on this data set, which is already a boiled down version of reality. So I would like to see researchers take this data set and determine exactly why all of our current approaches do so poorly on this already like boiled down reality. And actually, there's also another really interesting data set that came out. It's a new track, and it's from Spotify. I think like they sponsored the data. It's I think like 10,000, or I think it's 100,000 podcasts. And that is super interesting because it's dialogue. They have summaries for these podcasts. They just scrape the descriptions, I think. But the cool thing is when you're summarizing these discussions, each podcast is very unique. Like they have some latent structure in that people talk to each other, or like a guy is telling a story. But otherwise, they have not as many similarities between the topics or the way people talk, or any of that, honestly. And so when it's much easier to see if a model, especially focused around dialogue summarization, which is also what my data set is initially focused on, can generalize well.
But I love this because like it makes like gamifying stuff, uh like sorry like gaming metrics, because I mean
Mm-hmm.
D&D is a game, like a lot more challenging, because you're kind of like saying like, well, this is still relatively simple, like a human would
Mm-hmm.
understand this. But if for some reason all of your models fail, then that
Mm-hmm.
tells you your models kind of suck relative to humans, as opposed to, and this would be a counter argument to,
Right.
Transformers will be the trend for the next 100 years, like that. Like if they're going to do poorly on your data set, this trend becomes a lot more in question. But it would never show up in the standard benchmarks because no one was just
Exactly.
like
Yeah.
evaluating that question.
And so if you go through my paper, I have, especially in the related work section, I go through some interesting related work for dialogue summarization. And one of the papers that I really liked was this content selection comparison paper, essentially. And so what it shows is, and it's by McCohen from Columbia, and what it shows is that current models and approaches for summarization do really well when it comes to news summarization, which is what the community basically all kind of centered around when improving these deep models for summarization. It does really well. But then when it comes to data sets like Reddit or AML, which is this like other meeting data set, these non-news article, these non-like document-based data sets, they do really poorly. And this isn't even like rewriting and making a human readable summary. This is just picking out important information. And it's because in news data sets, they've shown that a lot of important information is just clustered around the front. So you can just take like the top 5 sentences and, you know, you've got a good summary.
Oh, like they've
And
done the work already for you. Like it's a way easier data set just by it's like saying, well, it's like saying I'm training a summary model on a data set on which the summary was just written down, and then you're like,
exactly.
why can't you
And not
figure
only
out?
that is that we've spent so much effort and so long on those data sets that our definition of summarization implicitly was centered around summarizing just news. And so this is where I'm hoping like data sets like mine will challenge that and say, well, if you can't summarize this data set, then truly your model has learned to pick out some important information in some domain,
Mhm.
but not this also incredibly valid, incredibly structured domain that
Like
should be
well,
easy for you to summarize.
like what I like this is it makes me a lot more optimistic about future work. Whereas with Transformers, like I felt like it's like, okay, well, either make it bigger or figure out ways to make it smarter. Like that should be the research direction. But I think after
Mhm.
this, like I'm thinking, well, like, oh wow, like wouldn't it be great, for example, to have like a summary model for like game walkthroughs? Wouldn't it be great to have a summary model for
Mhm.
what was the gist of this podcast, or like a summary model for what we just talked about, or a summary model
Yeah,
for
absolutely.
the storyline of a game? Like these are all very different problem domains, and the data does exist. It's just nobody has bothered to put it in a standard format, like kind of similar to the OpenAI gym interface, where it's like, well, here is consume the tokens from this thing. Here's a nice
Yeah.
API.
No,
So that's
absolutely.
awesome. Like,
And it might be that like transformers will play a core part in like let's say like we do somehow get the ultimate content selection model that is able to find important content in any kind of like text-based media. It might be that transformers still play like the core role in that. But my guess is that even if they do, we kind of have to fundamentally change the way that they're used or trained or fed in data or something about it. You can't just throw data at it, like unlimited data, and just expect it to work.
all right. So Rafe, I guess like we're kind of over at this point. So I want to ask you like one last question. It's a big question, so feel free to
Mhm.
take your time answering it. But I was hoping like you could kind of give some more career advice. Like let's say someone wants to get into ML, wants to get into NLP. Like how do you think they should really go about it and evaluating what's important? And then also like once they do end up joining a company, doing ML-ish, NLP-ish work, how do you think people shouldn't fall into the trap of just optimizing for promotions, or really like thinking about like what is actually important in life and work?
So I guess I've been thinking about that a lot myself. I think you asked like almost two independent questions.
Yeah.
One is like in any career, especially in like a information-based career where kind of like just you're behind a desk. And I think in those careers, you kind of have to figure out what you want from kind of like life and like how you want to live it. I think one thing that I've been really thinking about these days is not like pursuing prestige. Like I think that's kind of like a toxic mindset and it'll just like lead to ruin because you're essentially like waiting for a lottery win. Um, and I think my advice would be the first thing to let go of is trying to pursue prestige. So if you want to do NLP, don't do it because you want to be like super famous. Just do it because you enjoy it. Because and you're gonna make like okay money, like if you actually get a job doing NLP anyway. So I wouldn't worry too much about that. But you know, like don't try to be like a billionaire and do NLP for that reason. Just because that's really toxic. I think Then to get into machine learning, I've seen a lot of, well, first of all, I actually don't have a PhD. I only have a bachelor's from UIUC, which admittedly is a really good school. But anything that I learned in my undergrad at UIUC, you can learn either by yourself, or even if you went to a school that isn't like, oh, like top 5 computer science programs, you'll learn like everything you need from your school. So your school isn't your limiting factor here. And you don't need a master's, which I've learned, which I actually really wanted to. I was thinking, should I go to get a PhD or something? Will that like kind of like up my game? And I realized that what a PhD gives you is, if you don't have a lot of structure, it'll give you structure in your time. It'll give you more time, because at least like your time is somewhat like paid for. Like you'll get a stipend, so you're not going to be like starving, hopefully. And you'll have time to do research, and you'll have hopefully like a good mentor kind of like letting you know, hey, you're doing this wrong, you can improve on this. But actually that's what it gives you. It doesn't give you like some magical gate to like, it's not going to make you a better researcher automatically. It's still like mostly your work. And that's what I've also realized. And so if you want to really get into ML, the very first thing that you need to get good at is not math or machine learning or like any arcane skills, but you just need to be a really good coder or engineer. I think that's like your kind of ticket in. Unless you're an absolute genius researcher who's like brilliant at like math and doing all this stuff, then you don't need my advice at all, honestly. And so for most of the people who just want to do machine learning, one, get good at coding, because most of your impact will be through implementing your models. You can't just tell like an engineer, hey, I think we should use this, and that's not the end of your job, right? Like you're going to be way more effective and useful, and people are going to want to pay you if you can implement your own stuff, and more importantly, if you can debug your own models and debug your own infrastructure. I've seen so many applied scientists who they're smart, definitely, but they kind of freeze when they have to debug any code, and they're very irritating to work with. Just to put it out there.
Yeah, like this helpless attitude is very frustrating.
Yeah,
I've
exactly.
definitely
And the thing is,
experienced that.
debugging is not hard. Like it doesn't. You don't have to be genius. You just need to say, okay, I'm going to try and I'm going to debug this, and there you go. You're going to do it most likely. Then if you know how to code, good, and like if just keep working on those skills, and then as you learn machine learning, I think like you don't need to learn like all like the funny thing with deep learning is that it's easier than ever to get into machine learning now. It's not like where you need to know all this arcane math like you used to have to know. You just need to know more about deep learning, which kind of sucks in that like, does that mean we're getting dumber as a community? But it's also kind of interesting because I think like in the future, you are going to need to know oodles of like math again, just to understand what's going on once we kind of unlock the secrets of it. But for now, you just need to really understand what's going on. And there's like a bunch of good resources. The Andrew On course is actually really good to get you started. And then with NLP, I would say that just be interested in language, I guess, because deep learning and transformers and like all these complex models, they kind of have disrupted the field in such a way that you barely need to know any linguistics at all. Like you don't need to know much is to like get into this field, I guess is what I'm trying to say. You just need to be good at coding. You need to be okay at math, and you need to have a very critical mind. Like you have to be very critical in how you're evaluating your models, like what it means, how much value it'll add. And otherwise, I think like the best piece of advice I can give you is you need to get a really good mentor, especially if you're younger or you're just kind of starting out. You can learn a lot by yourself, but in the end, and very realistically, I think what helps you the most is if you have someone kind of showing you the ropes. It might be in your company that you join, or if there's no good mentors in your company, then I would actually suggest leaving and joining somewhere else where you can't find one. And I think actually out of all the advice that I gave, that's the hardest one, because I think that actually requires some component of luck.
Yeah, like I don't think it's entirely trivial. Like for example, I found it easier to find mentors when I was at UC San Diego, for example, as opposed to
Yeah.
Microsoft. But like with time, it did come, but it was hard to
Mhm.
basically find like what I like to call future me, which is,
Yeah.
someone who's very similar to me, but also a lot smarter and figured out a lot of
Yeah.
other stuff on their own. I haven't met that person yet, but I'm
Yeah, that
still
is really
looking forward
hard.
to
And
it.
actually that's one of the advantages of a PhD program is that you've put yourself into a structure where everyone's kind of incentivized to mentor.
Hmm. Interesting. Yo, Rave, like that was it for me. Yo, thank you so much for this. Like, I really enjoyed our chat. I'm hoping we can do a second one sometime soon. I'll keep you posted. But otherwise, like honestly, most of the feedback you gave was invaluable. I really especially liked your focus on actually moving like NLP forward, and I think better data sets is also to me a lot more interesting than better transformers. Just because, like, if I can't even run the damn thing because it costs millions of dollars, like, how the hell am I ever gonna do something interesting?
Yeah,
So
absolutely.
I think you've given me hope that there's still like low cost ways to have an impact in this field. So
I think
it's super
so.
inspiring.
Yeah, absolutely.
Thank you, Rafe.
Oh, and just as an interesting tidbit, when I
Mhm.
wrote my paper um, on the critical role Dungeons and Dragons thing, I have an experiment section where I try to compare the models or try to compare like recent models to see how well it does. The worst one to run for me, like you mentioned, was the Transformers because it
Interesting.
costs so much money.
Huh.
That's where to make it more usable for people even wanting to re-implement, I chose the model that was not transformer based. So at least people could reproduce results and run it locally if they wanted to.
There you have it. We have our first bit of proof that transformers aren't like the end of NLP. I
They're
love
not.
it.
They're really awesome, definitely, but they're not the end. No way.
All right. Thank you, Rafe.
Yeah,
That's
absolutely.
it.
Thanks.